Hello, today we're talking about how to diagonalize a matrix. So in particular, I'll tell you what I mean by that. Let me start by recalling from last time, kind of our quest here was to say, given an n by n matrix A, what we want to find is a invertible matrix P and a diagonal matrix D such that, right, we can write A as P times D times P inverse. This is saying that A is similar to a diagonal matrix, and we saw last time that this is useful for us. For instance, it allows us to calculate high powers. And what we also saw last time is that this can be done, this is possible, if and only if A admits a collection of n linearly independent eigenvectors. Okay? So, what this means is that the question of finding this, or finding this matrix P and D that will give me this relation, it comes down to the fact that how can I describe these eigenvectors? And in fact, the eigenvectors, eigenvalues determine P and D. Okay, and so I'll remind you of that in an example here. But let me do this with an example. So e.g., let's diagonalize the matrix A, let's say is 1, 3, 3, minus 3, minus 5, minus 3, 3, 3, 1. I took this example, I believe, from your book. So now, okay, so again, I want to diagonalize. What I mean by that is find these, I should say, if possible. So what I'm asking here is, if possible, find me a matrix P and D so that A is P times D times P inverse. So step one here, right, again, we're going to use the fact that this comes down to finding eigenvectors. Well, how do I find eigenvectors? As you know, we first find eigenvalues via the characteristic equation. So, well, what is it? Well, in general, it's going to be 0 equals the det of A minus lambda I. As you know, you take the determinant of this matrix. In this case, it would be the determinant of, let's see, A minus lambda I means I take minus lambda on the diagonals. Everything else is the same. All right, this 3 by 3 matrix, I take the determinant. It's a little bit messy, but with some algebra magic, this becomes the following factored version. So what this is telling me is the eigenvalues are the roots of this polynomial. Lambda 1 equals 1 and lambda 2 equals minus 2. Now, of course, there's something special here that this factor of a 2 means that this guy has algebraic multiplicity 2. This guy has multiplicity 1, right? So again, algebraic multiplicity is the factor, the degree of the exponent of this term corresponds to that root, and here we see a 2, so it has algebraic multiplicity 2. Okay, great, that's step one. Now, right, once we have our eigenvalues, we can get our eigenvectors. So step two, let's find eigenvectors by determining eigenspaces. Now, what are the eigenspaces? Those are the null space of A minus lambda I. So I have two eigenvalues here. For lambda 1, it turns out that this is the span of 1 minus 1, 1. For lambda 2, it turns out it's the span of two vectors. It's going to be minus 1, 1, 0 and minus 1, 0, 1. So if you go through A minus, sorry, this is for lambda 2 equals minus 2, right? So if you take A minus 2i, in other words, A plus 2i, you look at the null space of that matrix, you get this. The solution set looks like that. So what we're going to do is we're going to take eigenvectors. Remember, I can take anything that's non-zero in those eigenspaces. I'll take V1 to just be this matrix 1 minus 1, 1. V2 will be minus 1, 1, 0. And V3 will be minus 1, 0, 1. Okay? Now the claim is that the collection V1 through V2 through V3 is actually linearly independent, right? This is what we wanted to come up with, was a collection of eigenvectors that's linearly independent. And why is this the case? Well, first of all, if I look at just V2, V3, this is linearly independent just because, well, different ways to see this. I mean, you can take those two vectors, make a matrix, and look at the pivots and see that there's a pivot in every column. But it's also, another way to see this, this is a basis for the lambda equals -2 eigenspace, therefore it's linearly independent. Anyway, that's it's also since it's just two vectors, I can see that they're not multiples of one another. But what this again, what this then implies is that the collection of all three of them is linearly independent because I've now added a vector v1 that has a different eigenvalue. Since lambda 1 does not equal lambda 2, I've added a new vector that has a different eigenvalue that will always give you an independent set. Okay, so we've got a collection of three linearly independent eigenvectors. That's good news. We're more or less done. We can say that the matrix is diagonalizable, and in fact, we're going to take P to be, right, the matrix I get by taking those eigenvectors as columns. So what did I do? I take V1 was 1, -1, -1. Then -1, 1, 0, -1, 0, 1. I guess step 4, if you like, is to make the diagonal matrix. That's going to be, right, taking those corresponding eigenvalues down the diagonal. I should say that, I didn't actually have to put the order in as I've written them. That was an arbitrary choice to list them in this order. But once you write down your eigenvectors, what you have to do is match up the eigenvalues in the same way. So since this first column has eigenvalue 1, I put a 1 there. These two have eigenvalues, whoops, -2, right? So this will be my diagonal matrix. Okay, and we're done. That's the diagonalizing the matrix. You can now check, you don't have to do this here, but we can check that, assuming I didn't make any mistakes, that in fact A is equal to this matrix times the diagonal matrix times the inverse of this. And for, my purpose is you don't actually have to get that P inverse unless I ask for it or unless you're asked to use it somehow. But that's the idea. That's the that's the recipe for diagonalizing a matrix. Let me just end with continue with a couple of observations here. Again, we want to know in general when is a matrix diagonalizable, and here's one thing to point out: if A is an n by n matrix with n distinct eigenvalues, then A is always diagonalizable. Okay, so that's kind of nice because you don't even have to check anything about eigenvectors. You can just immediately, write down or conclude that this thing is diagonalizable. Let me just give you a proof of this. It's not too hard to see, right? So let me say you're assuming that we have n distinct eigenvalues. Let me call them lambda 1 through lambda n. Well, they're eigenvalues, so they come with at least one non-zero eigenvector for each number. Let's call them v1 through vn. Now, what do you know? This collection, right, this is what we just kind of mentioned before, is that this collection here is linearly independent. Right, because they each have distinct eigenvalues. We prove that in that case, the collection of eigenvectors will be linearly independent. We've got n of them. That implies, by previous results, that A is diagonalizable. Okay. Great. So if A is if A has all distinct eigenvalues, n of them, right, we're done. But just a warning: if A has repeated eigenvalues, then no information. Then we need to check what's called the dimension, well, what what we've called the dimension of the eigenspaces. Okay, so let me just give you an example. So, well, you know, just for the example that we just talked about above with, if you took A to be the matrix we were just looking at, which was what? 1, 3, 3, minus 3, minus 5, minus 3, 3, 3, 1. This had lambda 1 equals 1 eigenspace had dimension 1. Lambda 2 equals minus 2 eigenspace had dimension 2. But if you let B be the matrix, let's see, I wrote this down somewhere. Let's see. Here we go. So if you take this guy to be, let's see, did I write this down? Yeah, so this guy here, 2, 4, 3, minus 4, minus 6, minus 3, 3, 3, 1. It turns out that this guy has the same characteristic equation as above, also has characteristic equation given by 0 equals minus lambda minus 1 lambda plus 2 squared. But in this case, it turns out that lambda 1 equals 1 has eigenspace dimension 1, but lambda 2 equals minus 2 has eigenspace dimension 1. Okay? So hopefully that makes sense. So I've got a matrix that has the same characteristic equation. The eigenvalues are 1 and minus 2 again. Now what's going to happen is that, you know, this guy has algebraic multiplicity 2, and yet its dimension of the eigenspace has only dimension 1. And so what that's saying is when I'm cooking up eigenvectors, I can get 1 out of this guy. But since this eigenspace only has dimension 1, I can only get a single, you know, eigenvector with that eigenvalue. And so therefore I cannot get 3. I cannot get 3 linearly independent eigenvectors. I'm in trouble. So this matrix B will not be diagonalizable. Okay, so A was because I had the right number of linearly independent eigenvectors, but B is not. And so just to end, let me give you a kind of, you know, observation here. So what we just saw is a theorem is that if A has repeated eigenvalues, then A is diagonalizable if and only if for each lambda we have the algebraic multiplicity of lambda equals the dimension of the lambda eigenspace. Okay? So remember, this was the number, you know, when I take 0 to be ... there's a lambda minus well, question mark here, and the degree is the algebraic multiplicity. And then here I want to look at the dimension of the null space of A minus lambda I. That's the dimension of the null space. Okay, so I need those two things to be equal for this thing to be diagonalizable. It means I have enough linearly independent eigenvectors, and I'm good to go. Okay, so I think next time we'll continue this discussion. I'll probably give you guys a few more examples to think about. So we'll see you next time.